Okay, so thank you very much for this, for the invitation, and I'm very glad to be here. And I, a bit like a sports commentator, have to start talking while nothing goes on the pitch. I just wanted to set up my computer. It's always a great responsibility for us to, speak in front of many brilliant young minds who are going to shape the future. And of course, I always like to quote Claude. The interview I once heard about from a physicist, a French physicist, one of the heroes of mine, who, when he got the Nobel Prize for physics, so talking about Cohen Tanucci, he was asked by journalists, "So, what do you want to tell about the state of the world and things like that?" And his answer is, "Well, the reason why I got this prize was that I was locked in my lab, which happens to be, level -2 in the building where I'm working at for the last 30 years. And about the state of the world, I'm probably the less, not very well informed. I certainly have opinions, but they might not be, worth spreading too much in the media." So, of course, this is because he's a very honest person, but there is some aspect of truth in that. I feel that, you are lucky, you're happy to do science because you love science. You're lucky that your ideas worked out and that you got recognition by, with prizes and things like that. And then you get exposed to suddenly you have to inspire young people and be careful of what you're saying and what you're not saying. And it's always a bit difficult. Now, when I was thinking about how to prepare this lecture, I want to first start with some take-home, general messages which are not mathematical. But and then I'll talk a little bit about mathematics. Of course, all the audience, at least all the other speakers, know that they say, "Aha, here comes a math talk. Let's see what's happening because are we going to understand something apart from the fact that these are peculiar people?" I'm sort of lucky to be on the side of mathematics where I can at least claim to try to make up stories that sort of illustrate a little bit what we're doing without writing any formula on the board or saying anything about numbers. But before going to that, I just want to say a few words. The first one is that, well, maybe you heard this morning that I want to say that scientists are very diverse. Science itself is very diverse, and within any topic of science, you have a huge diversity of possible individuals and possible ways to function. And this morning you heard a talk by a young colleague who said, "Well, science is like a business." I don't think my science is like a business, right? So, there is space for different type of approaches to science. And in particular, we mathematicians very often, and this is sort of when we discuss with funding bodies and things like that, the way of functioning is slightly different than that of people in experimental sciences. If you are sort of in experimental science, you need to build up a group. You need, working force. You need money, a lot of money to get the machines and get things working on. In some sense, we are sort of the extreme opposite. We need as little admin work as possible. We in some sense, when we have PhD students or postdocs, we spend time with them. We explain with, a bit like children. You educate people. Giving them a lot of things so that in the future they can have their ideas of their own and build up their own ideas, but you don't use them, in terms of interaction for your own research. And in some sense, when you want, when I went to negotiate with the president of my the place I am working at present, I said, "I'm okay. I can come to your university, but promise me that you will never ask me to apply for a grant." Because of course, if they know that if I would apply for grants, I'd be likely to get it, and therefore, there will be a lot of money flowing in, and therefore, was no problem to hire me because I would bring in actually some money. And I was saying, no, I just need time for myself. I want the freedom to have postdocs if I want to, no postdoc if I want to at some point, and adjust the number of PhD students to be fairly low. So it's just to indicate that there are different ways of approaching things, different sciences, and within different sciences, of course, this is what I'm saying is not true for all mathematicians. There are different ways of functioning. Now, I want to just mention a few things about some old memories of mine. The first time I realized that there was something fun in science and mathematics was in primary school, and that was, and the reason was not that I got fantastic teacher who explained us very complicated, elaborate things, but she explained us something very simple. I asked a seemingly simple question, which for those of you who know these type of things, if you have two sets. If one set has more elements than the other, and if the other one has more elements than the first one, then they are basically the same. There's a bijection between the two. And so she explained that for finite sets, and I just asked a stupid question. Yeah, but if the sets are infinite, is it still true? And then in those days, internet didn't exist, nothing. And Chen said she first immediate answer was that, well, I think the answer is yes, but I'm not sure, I'll check at home. So that was first thing. You ask a simple question, the teacher said, I don't know the answer. And then the next day, in those days, there was no internet. So she had to look it up, in some Encyclopedia Universalis that she had at home. And she came back and she said, well, the answer is indeed yes, but I wouldn't be able to explain you why because I didn't understand the proof. And that's the best teacher ever, right? So you ask a simple question, she said, I don't know. The answer is yes. It's a simple answer to a simple question, but if you want to understand why, you have to study, and you'll be better than myself. That's sort of the main thing. In the same way, then when I had this fantastic physics teacher in high school, when she told us about Newton's law and things like that, and of course we mathematicians were always like way behind, right? Sort of I start saying, yeah, okay. Thank you very much. This is very good. We understand why the Earth goes around the sun. But how does the Earth know that? How heavy the sun is? And that it has to turn. And the force, how does it work? And then she said, well, okay, let me think. I'll come back tomorrow with some sort of answer. And the answer was, of course, not the one as a mathematician you would like to hear, because except, I want to understand why and how does it work, and not just that it works. And so that's sort of the general thing that you have to go pay tribute to the fact that you have to ask your own questions, and often you come up. But why? How do you come up with questions? Then it comes back to the same introduction as the previous speaker, which has to do you have to build on your own identity, who you are. What did you do? What did you do as a kid? What is it that makes you a special, different from the others, that makes that maybe you will have different ideas or ask different questions? And I'm not going to describe to you what I did as a kid. Of course, I like to play soccer. I like to try to beat my older brother at stupid games, whatever. But there was a standard feature in those activities, which is that most of what I found really exciting, and I was really, spending energy building my neurons upon as a kid, you can actually very, very, see everything of those themes in the mathematics I'm doing. I'm doing abstract mathematics. However, in this abstract mathematics, the themes I'm developing are actually, resonating very, very directly to the fact that I loved looking at stars. I loved this sort of infinitely small, infinitely long. I was asking myself, little question about time. Is time, how does it flows continuously, but this continuum, what is it? And these type of things. And I love to play random games with throwing dices and things like that. And somehow in my mathematical research, you sort of recognize all these different themes. In the same way that, some mathematicians, they love playing you know, they actually, one of the speakers of last year, you know, he still regrets that he hasn't become a Latin, you know, Latinist, right? Speaking Latin and the rules and all these things. And in his type of mathematics, right, which are sort of very algebraic and with, you know, functors and things like that, you recognize sort of the individual behind that. So what I want to say now is that sort of mathematics, despite being a very abstract thing, because precisely it's an activity that takes place in our own minds, it is a very individual driven science, and you have to find the questions and the answer in yourself in some sense. And that's one point. Now, another thing is that you always hear, you know, you have to think out of the box, ask different questions, do things differently. And then you get told how to behave as a scientist. You know, like you have to apply to this, you have to do that, you have to do that, you have to optimize your research strategy in order to get promoted to the next step, and so on, so on. And by doing that, you just get completely uniformized, right? So you're just doing it in a certain way. One feature that you know, 25 years ago when we went to a conference, when you went to a talk like that, well, first of all, there were no beamers. Okay, so the talks were, you know, sometimes handwritten slides, blackboards. You didn't have this visual aspect of, you know, being bombarded with images. And so you could see things like the handwriting of the speaker. You know, you had all sorts of more human parts that were actually, you know, detectable in the lectures. And nowadays, well, you know, you get these overflow of, you know. So, for instance, the way the presentations are done with Beamer, with PowerPoint, and so on, you know, everybody uses the same format. So, in the end, you think that, you know, the way to learn stuff is to watch a PowerPoint presentation. And then I remember, you know, when I have my topology class in Zurich or things like that, I tell them, okay, now everybody switches off really switches off your cell phone, you know, just to know it's off. You know, not that you have the possibility to take it out and have a look like some people I'm seeing here. Well, from here I can evaluate to 10% the number of people who are just playing on their smartphone, and they will, and you know, just having it in the box. And then I say, okay, now we're going to do mathematics by closing our eyes, because it's all takes place in our brain. You can listen, you can imagine things, but you don't have to watch. You know, to be, you know, a passive person by looking at what I'm writing on the blackboard. You have to reinvent things in your own brain, okay? And now, of course, yeah, that's sort of, you know, then you feel like this guy is crazy, this lecturer is crazy. But that's exactly the sort of, just to pull people a bit out of their comfort zone when you are sitting in an audience and trying to sort of stimulate different things. And for mathematics, there's a good reason for doing that, which is that we construct things with elementary blocks. In some sense, when we do a 2-hour mathematical lecture, math lecture, I always have the impression I convey one idea. You know, there's a proof with one trick at some point, and you have to understand that. It takes 2 hours to develop things, to, you know, make things in such a way that you know, the brain, you know, your brain gets and clicks and manages to do that. And for doing that, you have not to be distracted. So not writing grants, but also, you know, during the lecture, you have to be sort of, your mind has to be free and ready for that. And of course, if we get bombarded with, you know, lots of images and lots of gadgets and things like that, you're actually doing exactly the opposite, because we want to get, you know, the abstract, the essence of things. And for instance, and you don't need to have too many of these visual effects, like the type of thing that your brains are very much nowadays trained on with smartphones and jumping from this to that. You have to focus on one thing during some time. And as a result, you will not see many images or distraction on my presentation. I will try to, you know, be down to it. Okay, so now maybe comes the time where I want to tell you a bit of math. But don't worry, I'm not going to tell you math. In some sense, we're going to start with I want to tell you a little story which actually has incarnations in a number of applications. And what I want to say is just show you a little example which pinpoints a very special phenomena, which is at the core of some questions having to do with quantum computing, or some questions in theoretical physics, some question in, well, you'll see in, random, trees of evolution and things like that. So imagine, let's play this little game. You take one individual, and we're going to look at the genealogical tree of that individual. So the rule will be very simple. Each person, independently of each other, will have either 0 children or 2 children. And you will have 2 children with 75% chances and 0 child with 25% chance. Right? So in average, you have 1.5 child per person. Right? So it's sort of looks pretty good in terms of growth. And now I'm going to play this game that I want to show you my handwriting. Well, okay, you start with one person at the top, and that person, say, has 2 children. So, well, you just grow 2 children. One of those 2 children has no child, so this stops. And here you have 2 children. Okay, and then you just continue. That one has 2. That one has 2. Right, so in average, 3/4 of these dots will have 2 children, and you continue like that. And you see my handwriting is not good, especially on the like that. And you continue like that. So what can you say? Well, you can say something, the question is it possible? So that's a typical mathematical question, because nobody cares about infinity in terms of genealogy. But we know that life on Earth and so on is probably not going to be infinite, but we like to think about infinity. So the question is, if you play this abstract game, is it possible that the genealogical tree will be alive forever? So of course, the first answer, there are simple questions, right? Answers. First one, of course, if you have 0 children to start with, then it's game over. There's no infinite genealogy. And after any, even if you have like 8 grandchildren, 4, okay, 8 great-grandchildren, looks good, but maybe none of these, by accident, or by chance, and all of these 8 grandchildren have no children, and then it's game over as well. So, on the other hand, as I told you, you have 1.5 children per individual. So, in average, the number of people at the nth generation should be 1.5 to the power n. It will grow exponentially. So less obvious, but this is type of things you get you learn when you learn probability theory in the math curriculum. It involves things called martingales and things like that. So it's very easy to see that with probably actually the probability that the tree will be infinite forever is actually positive, and you can compute it. It's going to be 2/3. It's pretty simple. And with probability 1/3, the tree is finite, so at some point you become extinct. And most of the time when this happens pretty quickly. Right? It's because the first steps. Now, and the hint is just, I just let it, if you want to become extinct, either you're immediately extinct, 1/4, or you have 2 children, but then each of the 2 children have to have an extinct, finite tree, so that's why you have the p², and you just solve this equation to get p to 1. Now, with probability 2/3, the tree will be infinite. Okay? And now comes the non-trivial part, is that when the tree is infinite, that's the theorem by some Keston and Stigum, and Keston is one of the most important mathematicians of our time, who died last year. What happens is not only the mean number will be 1.5 to the end, the expected average number, but actually typically, when the tree is infinite, then indeed the size of the tree will be of the order 1.5 to the n times some random constant. So it will explode always in a certain way. Okay? So either the tree is finite, or it's infinite, and if it's infinite, you have information about the rate at which it sort of grows larger and larger. Okay, that was the first little story. Now I want to tell you a different story, which goes as follows. Suppose that you have 3 to the power n people, and we're going to, for the sake of this talk, I'm going to consider them as voters. So these voters, right, I'm trying to, slightly, stimulate your neurons at some point. So I have to, say little stories, wrap it up, and so on. But it's always nice to get neurons big. So you have 3 to the n voters. You'll see why it's a large number, right? Why 3 to the n you'll see later. But each of them is the outcome of a coin toss, right? So they're either white or black. Their opinion will be white or black. And each one chooses that with probability 50% to be white or black independently of the other, right? So it's just a sequence of coin tosses that you write like that, white, white, black, black, and so on. Now, the usual way some countries proceed to perform an election is to look, okay, who wins? Are there more white voters than, people who vote for the white opinion or than for the black opinion? And you have other systems. And here another standard system will be, you can make up here for the sake of the presentation here, is going to first group them by packs of 3. Why 3? Because it's the first, odd number after 1. Well, no, the first odd number at all, sorry. And you'll see why. You group them in a pack of 3. And each pack of 3 has 3 voters, so it's odd. So there's a majority. Right? There's a majority opinion in each pack of 3. Either it's 3 black, maybe say the majority is black. Either you have 3 black and 0 white, or 2 black, 1 white. And you can do this little thing, I'll come back to that later. So what you just do that each pack of 3 elects its own opinion, majority opinion, and is replaced by just one representative of that opinion, right, to the next level. So that way, you have grouped the thing by packs of 3. So you have m over 3 packs. Each one elects its, opinion to the next level, and now you have m over 3 individuals, which have a certain opinion. And if you think a little bit, you see, well, each of these m over 3 people is either white or black by symmetry with probability 50%. And then you do the same again, right? These m over 3 things, you group them by pack of 3, you look at the majority opinion, and you replace by an individual of this majority opinion. Okay? And because we started with 3 to the power n, you do that, until you have just one person left, which is the outcome of your result. Okay? Is that clear? So what the picture that you have in mind is something like that. Okay? So you start at the bottom here, either black or white, and here the white is just transparent. And then you build the tree up, right? You view it like a tree. Here 2 to 1, then it becomes black. Here 1 to this is white, this is black, and so on. Okay, and then you build it up, and then you have the outcome. Yeah, sorry. So then you have the outcome, which is black here at the end. All right. So for those of you who are mathematically oriented, or the general feeling is that first reaction, if you come from engineering or whatever, say, well, you have a function which is the outcome here, black. And this is a function of all these inputs. And this function, as opposed to this majority rule, is based on a very nonlinear structure, because you have this hierarchical structure, and it's a very nonlinear function of these Boolean inputs. Right? So that's a way to that you see around in many cases, and there are a number of applications of variants of this, and I'll come back to that in a moment, where these type of phenomenon, are actually occurring. Now, I want now to play the following game. Which is, the following question is going to ask, how stable is this outcome? The answer is black at the top. Now, imagine that maybe, at the bottom you do little mistakes. Maybe there are 0.1% of the small dots at the bottom are misread. Or that person cast the wrong vote because, they got confused or didn't understand something. Okay? And the question is, will that have a big effect or not? How likely is it that by changing 0.1% of the inputs, the outcome might be different or not. And our general, the rule of thumb is, well, change 0.1% of the inputs will not matter because it's the same way when you have a, voting system. It's very unlikely that you end up at 50.001%. It would be the, well, okay, so we'll come back to that. So now, forget about why I'm going to ask this question, which has to do with instability, but let's do the following game. I start at the top. I look at my top picture here, and ask the question, what's the probability that the top person was elected by 2-1 and not by 3-0? Okay. There are two options. Either it's 2-1 or it's 3-0. So, of course, you know that each of the three people that elected that person, just by symmetry, between black and white, and you can flip all the colors, each of these three descendants is actually black or white with probability 50%. I mean, of these three final electrons. And you do a little computation back of the envelope, and you say, well, the probability that it's 2-1, the election is 75%. It's 6 out of 8, and 2 out of 8, which is 25%, is the chance of having a 3-0, right? Because 3-0 means, you choose 3 times the same, thing, and you just do this little computation. Tails, 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 and the other one will be 1-8, 1-8. It's okay. 25% is the probability that the last election is won by 3-0, and 75% is the probability that the last election is won 2-1. Now, there's one little remark, is that if the last election is won by 3-0, if you change if somebody at the bottom of the tree changes his color, if you change something here, it will affect this one, but it won't affect those ones. So if the election was won by 3-0, you might, by changing one person here, you might change this color, but then the two others will still win by 2-1, and you don't change the outcome. So who can be, if you want to look for individual people here at the bottom, who can say at the end, oh, if I would have voted differently, the outcome would have been different. Then you need to win by 2-1, and you need to look into the descendants of those two. Right? But because if you want to change the outcome, one of these two here have to become white instead of black. Okay, so we play the following game. We start at the top, and we look, if it was elected by 2-1, we just look at those two. Now, was this one elected by 2-1 or not? Again, the probability will be 75%. If it's the case, we look at those two. Was this elected by 2-1? Yes. And we look at those two. This was elected by 3-0, so these three are not counted. Okay. So you just follow the tree from top to bottom of the dots that are elected by 2-1. You go from top to bottom. Now, what you end up with is something like that, right? You start at the top and we go down, and these green ones are exactly the ones that you see when you follow from top to bottom from the 2-1 elections. Is that clear? Now, if you do that, of course, you can do that all the way, much, much further down until you have 3 to the n, which is a huge number if n is very large. And you ask the question, will you have, will one of the dots at the bottom have the property that if it would have been different, it would have changed the outcome? Well, the answer is very simple. Is each of these green dots at the bottom has that property. Because this one elected this by 2-1, so changing it will change the color of this one. But this one was a 2-1 outcome, so flipping that will go all the way up. And this one was elected by 2-1, and then you go all the way up. Okay? So in this picture, each of the green dots at the end of the election will say, I should have thought a bit more carefully because I was the one who decided. Okay? Now, do you have many of these green dots or not? Right? Are there many green dots if the tree is very large with this thing? You know, at the bottom, now remember we started the other way around, saying we start with the 50% things at the bottom and we construct the tree upwards. Well, if you look at this, I just told you at each step, if you go from top to bottom, you are elected with 2 to 1 with a probability 75%. So this green tree, if you just keep the tree of green dots, is exactly the one we started with before, which was this random genealogical tree. Either you have 2 descendants with probability 75%, or you have 0 descendants with probability 25%. And that's exactly what this green tree is doing. And I told you, this green tree, if you go on forever, with 2/3 chances, will be actually infinite and will grow and grow and grow and grow. So when n is very large, with a large probability, you will have plenty of green dots at the bottom. 1.5 to the power n green dots. Okay. So that means that if n is very large, what you end up is you will have the property that typically, with a high chance, at the end of the outcome, you'll have 1,000 people, 1,000 green dots at the bottom, who have the impression that they are the ones who decided it. And they are right. They decided it. If they would have changed it, the outcome would have been very different. Is that clear? And of course, that's very counterintuitive, right? We feel like this cannot be true because not everyone can decide everything. But of course, the key point is that 1.5 to the power n is much smaller than 3 to the power n. Right? So in some sense, the system is deciding who's going to have the power, which are these special 1.5 to the power n points. Well, I'll stay put. That's okay. The special 1.5 to the power n points, which is a large number, but there's still a very small proportion of the others. However, if you have 1,000 green dots at the bottom and you misread 1% of the dots, you're very likely to have misread one of those. And therefore, the information, the answer you get at the end is not the true one. It's a wrong one. It's just a product of the artifacts of these, problems that you have there. Okay. So now I just want to. So this is what I just explaining it. So I just want to emphasize that these hierarchical constructions and these type of phenomena of big instability of the outcome, they arise in many more real world instances than we can think of to start with. And of course, when you understand something, then there's one question. If you want to target, you want to change for these hierarchical structures, you want then to change the outcome. Then then you have to find where the vulnerable point is. You have to know where it's not very clever to change the green, the inputs completely at random. You have to change one of the green ones. That's the important feature. And so there's a whole theory, and actually more in theoretical computer science, that has to do exactly with this question about Boolean function, and how to, the role of stability, the role of, you can ask a different question. A different question would be, if at the bottom it was not 50-50, but 50.1 times 49.9, which is the most, how sensitive to this slight perturbation of majority the outcome would be or not. And, in all these theorems, the usual thing is that the most stable and the most, the less noise sensitive thing is the majority rule. So there's a math theorem that says something like that. And it's not such an easy theorem, to come up with. So 2 years ago, at the International Conference of Mathematicians, there was one of the plenary lectures. So that means these people are selected very seriously about their scientific credentials. And one of our very nice colleagues from Israel, Gil Kalai, gave a plenary lecture. He's one of those people who investigated the mathematical side of these noise instability with respect to noise of Boolean functions. And you can watch on YouTube, these lectures are plenary lectures, or you can find them. And in essence, he sort of argued, I wouldn't say that, it's just more like the mathematical people who say, wait a minute, there might be a theoretical problem when you do quantum computing. Because in the quantum computing world, you are exactly dealing with things that are a bit less linear than you. So maybe you can do very clever things and but these outcomes might be very, very noise sensitive, right? So if there's a little mistake somewhere, then the whole thing collapses. You'll be able to do things very fast, but the outcome will be not the right one. So there's a theoretical thing that has to do that in the quantum computing world. There is the engineering thing, the constructing the thing, but there's a whole area having to do with error correcting codes and sort of how to handle the instability that has to be handled, and that is a theoretical obstruction where mathematicians and theoretical computer science people are actually working hard upon, because that's a big challenge. Gil Kalai, I asked him once during a walk. That's the best time to ask people to. You do a little hike, or you walk from the conference venue and say, okay, let's go through the park during 1 hour. It's a nicer walk. Ask him, do you really want, so what's your gut instinct? Will it work? He said, no. This is a theoretical obstruction. Of course, it's a mathematical one, which in some sense might not be relevant. As long as it works, right? If it's not because we can't prove it or something, but he was sort of saying maybe there is a actual issue. So this is just to explain that this sort of instability feature of these Boolean functions that are illustrated by this little story with this voting mechanism, actually there are some direct implication on the computer side. Now, of course, these are genealogical trees type things. So on the evolution aspect, you have these things. And also, it is related to sort of question and phenomena from physics, and I'm going to just elaborate more about that for those couple of you who, I don't know how many there will be, who enrolled for my session this afternoon. I'll elaborate more about that, but it is actually closely related questions and from physics, either from on the theoretical side or also coming from chemistry. So you all know, probably you have learned if you are a chemist or if that systems undergo phase transitions. So that you move the temperature at the macroscopic level, the structure of matter will be, when you change the parameter, when temperature hits a certain value, you will have a phase transition. Water becomes gas or something. Or iron becomes suddenly loses its magnetization if you heat it up too much, or at the Curie point and things like that. And then these critical phenomena, a couple of Nobel Prizes, got awarded to people who exactly, were able to understand what happens exactly at that critical point. That there were sort of universal features occurring at those critical points. Universal critical exponents that had to do with the way the magnetization of iron behaves when you go through that critical point. And what I was involved with in my research, which is understanding these fractal structures, that sort of type of structures that emerge at these critical points. Fractals are things that are, self-similar. So you have this sort of some sort of hierarchical structure type phenomena. And then again, you will have this idea that these random structures that are constructed by nature at these critical points, they will exactly, have exactly these similar features. And sort of, let me show you this following picture. Again, this is just a way to illustrate this by, more like a game type thing. But of course, it goes much deeper than that. So here's the following. This is called like what we like to call percolation. And by the way, this is what I'm going to tell you. It's not completely unrelated to graphene, the story I'm going to say here, because it is exactly these black and white dots that you have on the honeycomb lattice. So you have the honeycomb lattice, and what you're just doing is that each of the cells is tossing a coin independently from the others. So it's a bit like our voting thing. With 50% chances is white, with 50% is black. And I'm stuck because I said I would stay here, but okay, I'll just go here. So now we play this game where you draw this in white, and you draw this border in white, you draw this border in black, and that border in black. And for those of you who spend time with board games like I did, you immediately recognize that you want to play the following game, which is like, black wants to connect the two black sides together by a path, and white wants to connect the two white sides by a path, white path. And, you think a little bit and you realize that there are two options. Either white wins, and if white didn't win, if white didn't manage to make a path from left to right, then it means that black was able to block white by making a path from top left to bottom right. Right? So the way you see it is, if black didn't make it, well, you look at the outer boundary of the black island touching the top left. Well, it's made by an ocean of white that crosses and that makes the job in the other direction. Right? So you have two options. Whatever coloring you do of your lattice with black and white, either you have a crossing black wins or white wins. And one of the two has to happen. Okay? Now, here in that particular drawing, white won. There's a crossing. Okay? And each of the white or the yellow dots has exactly the same feeling as our green dots at the bottom that we had before. Each of the yellow dots thinks, if I would have been black, black would have won. Okay. Now, if you look at sort of the structure, what I've been involved with has to do with, the shape of these black islands, the boundary of the black islands, and these type of things. Clearly, the structure of these things will, be highly dependent on these, pivotal points that we like to call. And they are the ones who at the end say, okay, I had the following, I had the feeling that I got that. Now, I just want to illustrate why, our brain, you have to analyze yourself and say, okay, if I look at this picture, how do you see that white wins? Well, we have a way to function which is sort of linear. So you're going to follow and say, I can go and I make it. You're following some path. I could have shown you the same thing instead of, having some, not so large system. I could have the same picture with 100,000 things on, hexagons on side length. Then you have it's a great television screen. And the mathematical result, a little bit like the one I showed you there, was saying that these yellow dots are very likely to be very, very numerous. You'll have like 1 million yellow dots around. So in order to see who wins, you have to look simultaneously at all these 100,000 yellow dots. Otherwise, you wouldn't be, you have to be able to see them all at once. Our eyes can't do that. Our brain can't do that. Computers can tell us who wins, right? And so it's related to some of those questions that have to do with artificial intelligence and things like that we are, they can do things that we can't do, right? So this thing that, this way of thinking, of detecting these connections is exactly a very nonlinear structure that we are not able to control and not able to understand. And these type of features, as I said, would appear in any chemical, any phase transition dynamics that occurs will be of that type. Or many of them. Sort of. Physics and chemists would say, a second order phase transition would involve a phenomenon like that of very noise sensitive. Okay. So I just want to illustrate one, this pack. And of course now, having seen this picture, maybe you can see a type of child I was, what type of things I like to play and why I sort of was attracted by these type of structures. On the math and theoretical physics side, my main motivation is to understand what, when the mesh goes to 0, there's a continuum structure. These dots are not dots anymore. They are like become continuum. And what happens to these yellow dots in the continuum, right? Sort of how do you understand these type of structures? That's sort of the sort of granular material, structure within the continuum. And then I will conclude with the following thing, which is sort of orthogonal to a lot of what, our society, tells me to say. My deep motivation to study these things does not rely on the potential applications. I'm just looking for the beautiful math structure. Of course, this is very dangerous, right? So when scientists say, I just do nice, wonderful structures and I don't worry application, then, well, you'd rather think about what people are going to do with these, understanding these things, and maybe ethical things in finance and questions can be raised very quickly because these all things involving randomness are sort of could have applications there as well. But it's true that somehow I'm one of those people, and I'm not saying you have to be like that, but it's just to explain that these people exist. I'm just one of, because they are not, today's world, you don't hear that so much maybe. I'm one of those people who just says, I'm just looking for the beautiful math structure, and I'm very happy when I see a very nice proof. I don't really, the way to say I need money because it's going to be very important for the economic development and things like that is not my, it's not my driving thing. And I know that many of us, who chose to go in that direction for precisely that reason, because we like the science itself, not winning prizes, not, that was, when I chose to choose my path, that was sort of a different era than now in terms of the way the impact of science on society is and so on. And, maybe if I would grow up today, I would say, oh no, maybe I'd rather write poems, right? Or do something which, is not like a business, right? Because maybe, but still, I just want to say that there's a group of us who tries to, discuss with the funding bodies and discuss with presidents and so on, say, respect somehow the science also for just why we do it and who we are, and don't try to necessarily immediately see how useful we can be for you. And I've seen, in France, a number of French presidents, and it was pretty clear that their interests were not really respecting the science we do, because they would say, look at these things and say, why are you interested in that? These yellow dots, what's useful for? But still, you are a group of young people who are building up the life of tomorrow, and I still have the dream that this type of approach is important in today's society as well. Okay, thank you very much for your attention. I have a big